Noah Diech as our final speaker in the Beyond Carbon Neutral seminar series, which we've been running for 2 years now. We launched it previous academic year and have continued it through this year with the generous support of the university's Office of Research and Provost Office through an award they gave us as part of our distinguished faculty and faculty student seminar series. So I'm really just professionally and personally thrilled to be welcoming Noah here because he, in his own way, has done so much to raise awareness and continues to raise awareness around the country of the importance of negative emissions carbon dioxide removal. Long before I spoke with him or met him, I stumbled across his blog, Everything in the Carbon Sink, I think you called it, right?
Yes, indeed.
That he started, that then morphed into the nonprofit organization that he now heads and founded and has been building. So his title now is the director of the Center for Carbon Removal, which is a nonprofit organization dedicated to speeding up the development of CO2 removal solutions. CO2 removal meaning pulling CO2 out of the atmosphere. He's also a visiting scholar at the University of California, Berkeley, at their Energy and Climate Institute. And prior to getting started at the Center for Carbon Removal, starting the Center for Carbon Removal, he got his MBA from Berkeley's Haas School of Business. Before going back for his master's degree, he worked in consulting, getting experience in environmental markets, carbon offsets modeling, financial planning for power production, both renewable and fossil energy, energy efficiency issues, demand response, and a number of other areas related to energy and corporate sustainability strategies. So let's welcome Noah and look forward to a conversation with him about how we can build a new carbon economy. Thanks.
Thank you, John. Well, it's wonderful to be back in Ann Arbor. John and Susan, thank you so much for putting this all together. And I think we have been running in parallel, standing up carbon removal institutes, you all on the academic side and us on the nonprofit side, so it's been wonderful to collaborate, and I'm glad we can intersect here in person. I was actually born at University Hospital here in Ann Arbor. I left at about age 3 months, and it's taken me this long to come back. I hope to not be as long in between visits next time around, but it's just wonderful to be here. What I'd love to talk to folks about today is this idea of a new carbon economy, of how we actually continue to grow and have a prosperous society while fundamentally revisiting the relationship with carbon emissions, where we're sequestering more carbon than we emit. I hope that there's new content here for you all and potentially a new perspective on this idea of carbon removal. But I also hope that we have as interactive a conversation as possible. So I will request you all to raise your hands early and often to question and challenge. This is for you all, so I hope that the information here is new and valuable and can take this in other directions depending on all of your interests. So what I would like to get through over the next few minutes here is 3 things. First, who we are at the center, to just share a little bit more about the work that we do. Talk about what this idea of a new carbon economy is, and then conclude with how we turn this idea of a new carbon economy into a reality and just the economy of the future. And to discuss some of the emerging opportunities and trends that we are seeing in industry, in government, and in civil society across these pieces. My 3 key takeaways, there's a lot of info here, so I tried to boil it down into to three big takeaways. The first, we need to actually be sequestering carbon on net as a society. You all might totally get that. This might be a completely radical idea for you. I've gotten reactions anywhere in between, but that's the fundamental premise. The second piece is, in order to do that, there's this huge portfolio of opportunities on the land through agriculture and forestry, as well as in heavy industry. So figuring out how to deploy all of these solutions in a portfolio and figuring out how to create policies and systems change is essential. And then the last piece is, I genuinely believe that there is about to be a lot more activity and opportunity in this space. And it's never where I expect it will be, but I am seeing it emerge across many different sectors of society. And so what I'm hopeful to do is convince everyone here that there is a space for them in carbon removal in the future. Okay, so the Center for Carbon Removal, as John mentioned, we launched about 3 years ago as a nonprofit, and the proposition was fairly straightforward then, which there weren't any organizations focused specifically on carbon removal. Carbon removal was a big problem. We needed to change that. And the way we think about this change is three legs of the stool. So one is we need to change policy. So we're disincentivizing emissions and incentivizing sequestration. Two, we need to support commercial activity. So encourage corporates and investors and startups to bring ideas into the market. And those are the existing markets and policies that are out there today. And I think there are a number of opportunities that fit this bucket. And the third is research and development. This is the front of the funnel. Without lots of new ideas, we're not going to have the solutions that will end up being this economy of the future. And so we work across all three of those buckets. On the policy end, we function like a think tank where we help with analysis and translation. On the R&D side, we are establishing what we're calling the New Carbon Economy Consortium. It's a group of about a dozen universities that have programs like the Beyond Carbon Neutral effort, and how we can link those all together and marshal the funding for that. And then finally, on the economic development side, we're in the process of standing up a carbon tech incubator. So if there are any aspiring entrepreneurs in this space, please do reach out to me, because we hope to be able to provide the network and some initial seed funding for companies that are trying to commercialize the technologies that are coming out of this R&D space. Any questions about what we do at a high level, or where we're approaching this problem from?
Where did most of your funding come from?
That's a great question. We are philanthropically funded. So our main donors are an umbrella of foundations that focus on climate change under the Climate Works Foundation sort of umbrella, and a handful of high net worth individuals, their family offices. So we're a 501c3. All of our money is grant dollars.
So I'm curious, how you pick projects for your incubator? Is that something you had a chance to figure out yet?
Mm-hmm. So we're in the process of developing the specific evaluation criteria, but the main criteria that we have is twofold. First, does it make money? Is it a viable business? And two, is the sequestration potential of the solution actually reduce emissions? We're not focusing on negative emissions technologies from the beginning.
Interesting.
It simply has to be a pathway to negative emission solutions.
And is there a bar there?
Is there a bar?
Like it's got to reduce emissions by, for you to consider it?
No, we're hoping that the bar is not necessarily a bar, but a ceiling. Can you demonstrate a credible pathway about how the technology that you're building today fits in existing markets? But once you have developed that solution, you'll be able to more easily develop an actual negative emission solution.
Right.
And the quicker you can get to negative emissions, clearly the better. The more money you can make, the better. So it's an intersection of those two pieces.
Nice.
But in every one, it's how do you take waste carbon and turn that to value. And so we're thinking about it very broadly initially so that we can really create the ecosystem around here and begin to move investment dollars into this space and then eventually down that LCA chain into the systems that are actually sequestering carbon on net.
So are there any are there any publications or information that you're basing your searches on? I mean, that you know, if you look at things in Drawdown, you know, the book Drawdown, you know, it tells, you know, it tries to tell you what the impact is of many different human activities. Okay? And so that'd be one place to go to say, where are the opportunities? And, you know, I mean, if cows fart a lot, maybe you make something, a probiotic for cows that helps that problem, okay? And you sell it to Monsanto as an idea or something like that. I mean, are there other sources than Drawdown to give you kind of a perspective of the different weights of impact of humans on CO2?
Yeah, so I think there's a number of academic reports. In particular, the Secretary of Energy's advisory board came out with a carbon utilization pathway study at the end of 2016, I believe. Lays out a lot of the different pathways, and on our website we have a compilation of a lot of the key resources there. But so onward to a new carbon economy. I think the easiest way to describe the new carbon economy is in contrast to the old carbon economy. This is a great graph of GDP throughout modern human history. And we are particularly fortunate to live in this massively plentiful period of growth. But there's a strong correlation to that growth with carbon emissions. And basically all of our economic growth has seen a corresponding rise in CO2 emissions. What I didn't realize approaching this problem from a business perspective was the scale of the amount of CO2 in the air. That we have put around 2 trillion tons of CO2 cumulatively into the atmosphere, which is a staggering amount. It's roughly double all of the coal that we have in the world that is remaining that we have figured out. And we emit roughly 50 billion tons of CO2 every year, CO2 equivalents. In comparison, the total stock of cars in the world, there are about 1 billion cars, so at about a ton each. The sheer volume of CO2 that's in the air is staggering. This is a problem because CO2 is not the standard pollutant. That I come from a background of energy modeling, and we worked on criteria pollutants, the precursors for acid rain and ozone. And with these pollutants, when it rains, those pollutants come out of the air. So cumulative pollution doesn't matter as much as the rate that pollution is flowing into the air. So you essentially stop putting sulfur into the atmosphere, you stop having acid rain. Carbon is different because it's sticky, and that carbon stays in the atmosphere for a much longer time. And that of this 2 trillion tons of CO2 that we've put into the atmosphere, roughly 40-45% of it has remained in the atmosphere. The rest has gone into the ocean, causing a whole other set of problems around acidification, and the remaining fraction in trees and biomass. So this is a huge problem because we can't simply stop emissions if we actually want to clean up the problem. The problem won't take care of itself naturally. We'll actually have to not just stop, but then clean up the remaining fraction. How does this bring us to the new carbon economy? So this is the OECD's long-run growth forecasts. I don't think it's particularly surprising that they expect the global economy to continue growing indefinitely into the future. I think that's something that would be a good thing to have. But the relationship with CO2 fundamentally has to change if we're going to meet our climate goals. and I apologize for the messy slide here, but this is a summary of recent integrated assessment modeling. So economic optimization in the IPCC's latest climate reports. This is essentially a synthesis of all of the scenarios that they ran to model what it's going to take to actually meet the Paris Agreement climate targets. And in the vast majority of scenarios, global emissions have to not just come down, but actually go below zero around mid-century. And this to me was, at least a few years ago, something that was quite shocking. I hadn't heard that anyone in the world was thinking about actually eliminating emissions. I had heard 15% reduction targets, 25% reduction targets. People were aggressive, saying 80% or 100%. But what we actually need to do is 120. And we need to do so fairly soon, by mid-century. That level of ambition, even though it's coming from this very messy integrated assessment modeling construct, I think is a radical shift in how we as a community think about climate change. Questions on these IAMs and what they're showing us? I know this is not inherently a clear construct. I myself am a recovering modeler, so this was a natural thing for me, but the global economy represented in linear optimization is not always straightforward. But okay, so what does this actually mean? Yeah, oh sorry.
You know, it's a question, comment, but every time I see this graph, I just look at those negative emissions and say, right, that's gonna happen. Like even starting at 2030, like that's really gonna happen. I mean, it's my understanding that the models, that's mostly facts, you know, bioenergy with carbon capture and sequestration, and I just don't see it.
So a couple of clarifications on these models. They are not projections or predictions. They're simply the outputs of optimizations.
Right. But what is needed, right? They're trying
Well,
to say
so this
what's
is
needed.
saying the economically optimal way to meet our climate goals. It's not saying the best way. It's not saying the most plausible way, the most feasible way. This is the least cost way that model. That model knows nothing but cost.
Okay.
And so it tells you what the cost is. Those realized negative emissions, it's essentially a black box. The model itself doesn't know technologies. It just knows parameters. And so in the model itself, it includes something called bioenergy with carbon capture and storage, but that's a very highly stylized construct. Nobody believes that this will be that technology. This is simply a representation of, you give the model a technology with this carbon removal potential at this cost, it will produce the amount of carbon removal at this scale. And so this is very challenging because many people see this as a projection or a forecast, and it's not. And I think that's a critical piece. It's an important tool that this tells you what the cost-effective way is, but these scenarios are only valuable in so much as you run variations on those scenarios to see what happens if the cost of negative emission technologies are more, or their availability is smaller, or we get lower cost renewables than we thought possible. So that's where it's almost misleading to show a single average of scenarios, because what's valuable is to have a baseline and then to show differences. But yeah.
So is this towards a particular climate objective, or is this incorporating economic costs of climate change into the model?
So this is a global model that says assume certain levels of economic growth, technology development, population growth, some of these basic factors. What is the least cost way to meet the 2C carbon budget? So it's all around carbon budgets, and I believe this is the budget associated with 66% probability of avoidance. So again, differences in avoidance versus exceedance in these carbon budgets, and 66% to me seems a scary confidence factor, but that's what these are showing.
It's easy to point to that rapid peak at about 1995 or so. What caused that?
Rapid peak.
See that peak in the gray? 1995 roughly. Is
Yeah,
that just
I think
data fluctuation, or?
I'm not sure if it's a data fluctuation or if it's a macroeconomic trend.
What, a cow fart?
Yeah, a lot of them.
Aren't there weather, like as a volcano sometimes?
So this is actually CO2 concentration, not solar. This is not a heat index.
There's like some weather events that sometimes strike.
That's true. I think they mostly influence solar radiation, so the watts per meter squared. But I guess
if
they
you
also.
don't know, I mean, it's, I'm sure it's there, but it's just kind of interesting. What would cause something to rise that quickly?
So does that also put a lower bound on projected costs of achieving these goals? I mean, can you put a number to that and say it will cost X?
Mhm. There is a total system cost of meeting that goal. I do not know what the total.
How
cost
can
is.
you have a total cost if you don't know the mechanism of sequestering CO2? I mean, you assume 100% efficiency in converting CO2 to something else, or?
No,
I
you-
don't know
yeah.
I don't know how you would estimate a negative cost if you didn't have a mechanism for.
So the way this estimates costs is what would the economy look like without a carbon constraint? What does the economy look like with a carbon constraint, and how much does it cost to get you this system?
Yeah.
And it minimize all of the infinite possibilities. It attempts to minimize this cost
So is that
mathematically.
without technology change? This is saying with, like, currently if we cut off all the CO2 production, what would that cost? And how do we optimize that?
And I
over
don't
the
see any
next-
dollar sign for anything here on the graph, so I don't know where cost comes in.
It's the minimization.
Yeah, you can, in the model, there's an implied total system cost.
What-
It-
Oh, okay.
You know, what the model has in it, that these models have representations of all sorts of technologies. So there's a
Okay.
parameterized representation of the cost of solar energy. There's a parameterized representation
Okay.
of the cost of nuclear power. There's a parameterized representation of the cost of hypothetical negative emissions technologies, as Noah pointed out.
Mhm.
And so there's a mixture of costs of things that we have good confidence in, like we have pretty good ideas about the cost of solar and where it might go, plus things that are simply best guesses by technology forecasters. And then these models put all those together and they're parameterized. So as Noah said, there's different scenarios of different mixes of costs. So that chart's a composite. And so as he said, it then looks for the least cost way. A specific model run with a specific set of parameters solves for the least cost way to get down to the 2-degree, the emission budget that we think gives a 66% probability
Yeah.
of remaining to 2 degrees.
So here's
yeah.
here's another way of thinking about it that's much simpler but potentially scarier. This is from a Rockstrom et al. Paper a couple years ago. Basically said that what we need to do is cut in half global emissions every decade forever, starting in 2020, while also roughly doubling carbon removal starting at the billion-ton level in about 2030 for the next few decades as well, if we want to meet our Paris Agreement goals.
So that removal's a relatively minor fraction of that, at least until 2050-ish, right? Like, the removal now isn't gonna have a big impact, even scaling at the rate you're describing.
Right. So the removal piece is starting from what I would describe as kind of solar back in the 70s or 80s, where you have the technology, it exists, but it really hasn't been deployed at a level that ranks on this graph. And I think the scary thing to me is I have never seen that red line described by any reasonable person describing how quickly the global economy is going to decarbonize. And that every increment, or as the slope of that red line gets flatter, the slope of the blue line in carbon removal has to get steeper. And so both are incredibly ambitious, but also necessary components. In theory, you could just draw a super straight line down and say, all we're going to do is flip a switch and turn off emissions immediately, but I don't think that's a remotely credible outcome that would be endorsed by anyone that actually works on this stuff.
But if you did eliminate CO2 emissions instantaneously, how many hundreds of years or thousands of years would it take to bring the carbon dioxide down to an acceptable level?
Well, so acceptable level is different for everyone. It will take hundreds of thousands of years to go back to pre-industrial levels,
Okay.
but it's a sloping curve. So the mean residence time of carbon in the atmosphere is 100 and some odd years.
Right. Yeah, but you have.
But that's
if you
a
have the
very
trees
weird
that- If you have the
construct.
trees that, aren't they sucking it down for you? It
Yeah.
isn't just going to dispel into space.
Yeah, so it's a curve that takes
Okay.
hundreds of thousands of
Okay.
years. Because what is fundamentally happening is the rocks that would naturally soak up CO2, that's the process for cleaning up. And rocks sequester carbon very slowly, which is a great thing, because if they did it quickly, we wouldn't have any CO2, and that would be a very bad thing, because it's essential to have at some concentration. It's just not going to be able to rebalance as quickly as we would otherwise need.
So what's the currently accepted ppm target coming out of the Paris Agreement? I know
So-
2 degrees C, we talk about temperature, but really it's about parts per million, it's about the mass balance. So
Yeah, so
what's the
the
currently accepted? And that number's may moved around as well, but what are we thinking?
it's
right
in
now?
the 450 ppm
Is
range.
450 still? Okay.
Yeah.
So in that Nature Climate Change paper, in the early 2060s, we hit peak atmospheric carbon, because that's when we start going from positive to negative emissions, right? Where that line crosses.
Correct. The
So
black line.
what's the overshoot? Because clearly we're going above 450 ppm.
Right. So the carbon budget as a fixed stock for that 2C limit is about 800 billion tons. We emit about 50 billion tons a year today.
Mhm.
So they think it's roughly 500 billion tons of overshoot for that 2C. Maybe these models vary dramatically, but a couple hundred to a couple thousand over. And if the 1.5C carbon budget is only about 200 billion tons, and so at current rates, that's gone in less than 5 years. So the overshoot for that will be way more significant.
So peak concentration will be what then?
Somewhere less than 500,
Okay,
most
high
likely, but
400s.
over 400,
Okay.
roughly. Yeah.
So if net negative emissions in the future is a key part of this trend, that's gotta be really sensitive to this technology projection of like what we are capable of sequestering, right? So like, if we can do it faster, then you can overshoot by more. If you have to do it more slowly, you can.
Yes, that is a generalization. I think there's a time value of carbon, that the global warming potential of carbon, if you emit it now, contributes to the temperature increase, and that will cause non-CO2 impacts, melting ice that can't be reversed, that sort of thing. But yes, in theory, thinking about it purely as a carbon budget without any sort of discount rate for that carbon global warming potential, that's roughly where you get to. All right, so here's my beautiful PowerPoint skills. And what I'm trying to show here is that there's a relationship between the existing piece of cake that we know as climate mitigation today, as well as a set of interrelated carbon removal pieces. And that you need the whole cake in order to get to any of the carbon removal objectives, as well as these deep decarbonization objectives. Because it doesn't matter if you scale up carbon removal slowly if you don't reduce emissions dramatically. And so it's not an either or, it's an and. And so the solutions break into two main buckets, one being photosynthetically driven and the other being chemically or technologically driven. So trees are nature's oldest carbon capture device. Couple 100 million years of R&D, field tested, like they work. Replicating that process, expanding the coverage of trees is something that has enormous potential. Soils store a massive amount of carbon. The total stock of carbon in our soils, something like 3x the total stock of carbon in our atmosphere. So the reservoir itself is huge. Soils build up slowly. So it's a little more challenging to be climatically relevant there, but an essential piece. And then you get into the mixture of the biological with the technological around this idea of bioenergy with carbon capture. So plants suck down the carbon, you convert that carbon into energy, and in the process of creating energy, either fuels, heat, or electricity, you capture the carbon and store it underground chemically. The alternative is essentially renewable carbon capture. You take carbon and you filter it directly from ambient air, power that with clean energy, and you can store that carbon as well. Lots of different variations on those themes. None of these approaches are radically different from what we do today around reducing emissions. There are decades worth of work and scholarship around how you conserve forests and agricultural systems. That work is essential, and it's the flip side of how do you expand and grow carbon in those systems. We've been doing carbon capture on fossil energy for decades and storing it underground at the million-ton scale for decades. We know how to do it there, and carbon is carbon at the end of the day, so we have a lot of practice with systems that are relevant for bioenergy with carbon capture or direct air capture. The one significant exception there is on the rock weathering piece. This is essentially grinding up minerals that would naturally react with CO2 in the air so that they sequester carbon at a human relevant timescale as opposed to the geologically relevant one. We don't really do that or anything similar today, but we have plenty of expertise crushing and transporting rocks. We have plenty of expertise drilling and fracturing rocks. So there's no nuclear fusion in this portfolio of things that require massive engineering hurdles to overcome before you even get the first one. I think the really interesting piece about this is when I thought of carbon capture prior to coming to this work, to me that was a fossil energy solution. That there was no way that we'd eliminate fossil energy, so we'd have to put carbon capture on it to clean it up. But when we talk about carbon removal, carbon capture is in fact a renewable energy solution, that it only really has that very deep negative footprint if it is powered with clean energy. So you can think about coupling wind and solar, the whole host of clean energy solutions that are out there as a source to power carbon capture. And that to me is a really interesting change in the dynamics of how we think about our portfolio of mitigation technologies, because it pits the carbon capture in a much less antagonistic way with renewables. In fact, the opposite, they complement each other, that the demand for renewables conceivably could grow quite substantially if we also demand carbon capture from the air.
So if we know how many joules it takes to create a unit of carbon dioxide, okay, and maybe it needs X joules if it's efficient like a natural gas, and needs 3X joules if you're burning coal or something like that. What, with the solutions that have been proposed, is the inverse? If you say, if I have solar energy, how many joules does it take to achieve that same
Hold that for
amount of
one
carbon dioxide,
slide.
but not emission, but
Maybe 2
sequestration.
slides.
Okay, okay.
First on the the biological side. This is a super messy graph, but I think the interesting thing about it is there is a ton of biological solutions for sequestering carbon at a meaningful scale. The x-axis at the top is in gigatons per year, which is a big number. That's the billion ton per year number that we're looking for climatically relevant. I think the other thing that jumps out is if you want to sequester carbon via nature, forests are where you go. That the amount of potential in restoring forests is enormous, and planting new forests is enormous. The other thing is this is both layers of that cake that I showed earlier, both avoided conversion as well as restoration and expansion. Roughly 50-50 the opportunity. So the rule of thumb that I can share from this is that if we had to say $100 a ton carbon price globally, again, big assumption, you could in theory unlock roughly 10 gigatons of natural climate solutions per year of climate mitigation potential. An enormous number considering we're at 50 today. That this was really surprising to me and significant. The last piece is the error bars are still quite large for all of this. The potential could be much greater and or much more limited, and it demands that we actually deploy these solutions and couple them with science to a much greater degree than we currently are.
Can you help me to interpret the coloration of those bars? What is?
Yeah, so the coloration is intended to show the co-benefits, and down here the air.
The climate mitigation key. there.
Sorry. So this is showing you the maximum potential, which is the furthest bar, and they included safeguards. So how do you make sure you're not covering all of the world's agricultural land with forests because people need to eat? So it's kind of what's the maximum reasonable number. The light gray is what you need to hit a 2C ambition.
So they've optimized and said this subset is the most efficient way to hit that.
Yeah.
Okay.
And then they've further optimized to say what's the lowest costs.
So it's interesting that reforestation doesn't have any of that low cost fraction.
But the avoided forest conversion does.
Sure.
It's the vast majority.
Got it.
Yeah.
It sounds like this would be really sensitive to population, so what sort of assumptions are being made?
So this is a several year long TNC-led study. It's a meta-analysis. So they basically looked at as much data that they could find on.
What I'm saying, like, is it based on estimates of continued population growth? Right.
So this is just taking the sort of biogeophysical limits of some of these solutions and assuming certain amounts of available land. I don't know.
Yeah, I guess I thought available land would have to be related to population.
I don't know if there was a consistent set of assumptions. I doubt there was, given that this was a meta-analysis, but all of it was published, so there presumably wasn't crazy assumptions on any of that. But maybe that's a not relevant assumption. So this starts to get at the technological side. So if we think of the past slide as being how can photosynthesis contribute, this is a representation, a number of different dimensions of the technological side. I think the bottom x-axis is a particularly interesting one. It shows which of these solutions require energy and which of these solutions actually produce energy. So you can see things like bioenergy with carbon capture are energy production systems that sequester carbon, whereas direct air capture systems require energy input. The land considerations are also significant. That's the color of the bubble. So green being low land requirements. Yeah. But what they're trying to say is that you can have these technology options like direct air capture systems that use renewable energy, fairly land intensive, they don't require a lot of land, but they do require a lot of energy. EW, enhanced weathering. So this is that rock weathering approach. On the other hand, if you want to use bioenergy, you're going to use a whole bunch of land because the crop production is very extensive, but you're going to make energy. So it's really a trade-off of what you're trying to optimize.
What are the blue droplets?
Blue droplets is how water intensive they
Okay,
are. Is that
okay.
not listed? Yeah.
And what's the size of the dome?
The size of the
Direct air capture is very big.
that means
I think that's cost.
is that cost?
Cost is in units of energy.
Maybe the challenge.
I think the size of the dot represents the energy intensity.
Isn't that the x-axis?
That's the x-axis.
That's a good question. I would bet that is cost actually.
I think, isn't the land requirement something right? That's the color.
That's the color. Yeah, it's a 4-dimensional graph that
I'm sorry.
humans are just
It's very creative.
easily able to internalize.
And AR is what?
Afforestation and reforestation. So that's the link back to the natural world.
Mm.
And so is that a range?
I think those are midpoint estimates.
Well, because there's, the AR has the two.
I think it's a range.
Oh, sorry, yes. So I think the interesting thing again about this is we know there will be learning curves for all of these technologies. We just don't know what they will be. It's very difficult to predict ex ante what the slope of any of these learning curves would be. Solar, batteries, I think both have exceeded expectations of analysts initially. But the key thing here is it's based on deployment. This is not Moore's Law, where every 2 years the price comes down. This is a deployment-based thing. So if it takes us 2 years to get an order of magnitude more deployment, or if it takes us 20 years to get an order of magnitude more deployment, that's the essential variable for us learning how quickly these solutions come down the cost curve. They do exist though. This is a direct air capture machine. It's a 50-ton per year unit, so every year we emit 50 billion tons. So this is small, all things considered. It looks big, but we need a lot of those. It is installed and working at a geothermal power plant, and technically this is the world's first negative emissions power plant with a total carbon removal of 50 tons per year because the geothermal system captures and re-injects all of its CO2. So this is happening today, but again, this is kind of the solar panels back in the 70s, 80s, that type of stage of development where tech exists, the early companies are there, the scale is not.
Does that directly use geothermal energy, or you have a conversion to electricity as an intermediate?
It's electricity.
Okay.
I think they might take some heat as well, I'm not sure. But mostly electricity is their cost, at least.
So it compresses the gas?
It does. And it's an amine-based system that I believe uses a temperature and pressure swing, combination of the two.
And that's the purpose of the box behind it, is that's the tank for the compressed gas?
I think the tank actually goes underground, and there's a pipe that runs to the CO2 injection unit. But this is really cool. This is in Iceland, and they inject into basalt formations, which is fairly unique. We mostly think about injecting in underground aquifers, and takes hundreds of thousands of years for that CO2 to turn into rock. these basalt formations turn CO2 into rock very quickly, on the order of years. And so it's actually a novel system, not just in how it captures carbon from the air, but where it puts the carbon underground.
No, it's pulling it out of the air, the CO2.
Uh-huh. That's the filter.
Production water from geothermal has some carbon dioxide in it as well, and that gets vented, I would assume.
Not in Iceland. They have
Water, what is it?
The geothermal hot water that you pull up from the magma formation, it'll have CO2 and ammonia and hydrogen sulfide, all sorts of,
Like is it higher than air?
high
Yes.
enough to be corrosive and noxious.
It
Lot
this
higher than
is
air. Yeah, much
a
higher.
facility that captures that CO2 and it re-injects it.
Yeah.
So
So it's actually a concentrated source, not a 400 ppm source.
correct. Yeah.
So it makes sense to do it, especially.
But to be negative, it'd have to be also pulling from air.
That's right.
Well, it
doesn't
says
Iceland
capturing
actually-
CO2 from air, so does it?
So
do
this
some of
box
both?
is the air capture component. Around the corner there is the capture from the hundreds of megawatts of geothermal power.
This wouldn't really be needed in Iceland because they're getting their thermal power right out of the earth.
Right, so this is a power sink, not a power source.
Right, but it's taking it out of the air, you said.
It's
But they
taking
don't
carbon
just-
out of the air and just
Right.
burying it.
Right, but they have nothing, if they're getting all their heat out of the ground, they'd have nothing putting carbon in the air.
Right, but we all put a lot of carbon in the air.
Oh, you mean from everywhere else?
Yeah.
Okay. All right.
Iceland's doing the world a favor. Yeah.
Yeah.
Thanks, Iceland.
So is it true that some power companies want to do this sort of thing, but then use the carbon dioxide to extract oil from wells which are depleted, or is that just a rumor?
Oh, so they're,
No, I'm doing it already.
yeah.
Petronova in Texas. does
Okay,
that.
okay.
Yeah, there's a long history of using CO2 to make oil. I
So
don't
the
believe
net-
that
so
anyone-
the net CO2 is of course positive once you burn the oil too.
Probably not,
Oh.
because you're displacing more carbon intensive oil, most likely. There's analysis that tries to do that systems analysis, and it has a net reduction. It's not net negative. It's still a overall positive footprint.
Yeah, okay.
It's just lower. Yeah, I don't believe anyone is using air capture for that just yet. These systems right now, yeah, $500 a ton, plus or minus a couple $100 a ton. But as the first system, like this is the first one. If you want to put CO2 into an oil field, somebody will buy that for $15 a ton. There's a bit of a gap. But if you think about solar coming down 100x in price, even if you only get 10x reduction from $500 a ton, all of a sudden it's a reasonable technology in the broader social cost of carbon yardsticks. Okay, so let me pause there before I get into the how do we actually turn this into reality. Questions on any of the solutions, on any of those pieces? Okay, now we'll get into the fun part then. So this is actually, the idea of a new carbon economy is slowly starting to creep into the broader conversations that we're having, policy, business, and civil society. So I'll start here with the policy landscape. First is that the Paris Agreement actually has a fairly big mandate for carbon removal. It says we need to keep temperatures well below 2°C. As the modeling shows, basically the only way to do that is through large-scale removal. And the language of the Paris Agreement is a little bit ambiguous. It says that countries should aim to balance sources and sinks. And so carbon removal is that sink component, though the lawyers have not gotten to the bottom of exactly what all that means and what it implies. That said, on the international level, there isn't that much in terms of policy that's happening today. There are on the order of $10 million per year research programs in Europe. That is significant because they were zero a couple years ago. But it's not significant because we need a lot more. And if you think about the Department of Energy having billions of dollars per year in energy research, the amount that goes to this is tiny. The federal policy environment has been actually surprisingly opportunistic in the past couple of months even. That, believe it or not, Congress and the administration just enacted a fairly significant federal carbon price for sequestration. It's in the form of a production tax credit. It's called the 45Q tax credit. If you bury carbon underground, Uncle Sam will give you a tax rebate of $50 per ton for every ton of CO2 that you store, assuming you meet some conditions of minimum size and so forth. But that's huge. The carbon price in California, $12 a ton. In the Northeast states with Reggie, with $5 a ton. So the fact that we are literally paying people a carbon price, this is a bipartisan bill signed by President, passed through both houses of Congress. To me, that's really significant and shows the bipartisan potential of these solutions.
Is there a ceiling to that
No,
program? No.
Yeah.
at least 3 9.
There's a time cap. It has to be, a project needs to be implemented in the next 7 years. You get the credit for 12. But as a first step, it's pretty meaningful.
How does that compare to current costs for storage with reasonable technology?
So there's some interesting papers out there. If you look at the lowest cost of capture systems, it's most likely ethanol refineries. They produce pure CO2 as you ferment the grains. $30 a ton compressed and stored at any meaningful volume. So that's well within this range. The power plants that are out there are probably $75, $80 a ton. Current prices, I would guess that's for coal power. Natural gas is fairly close these days.
So then it depends on capital requirements, like people would be putting this in place at every ethanol plant, it sounds like. If they're making-
You would think that, yeah. I think we'll see a lot more projects. They need to be a minimum size, 100,000 tons for storage. So that, I mean, there are only a couple hundred ethanol facilities in the U.S. A few dozen are above that minimum size, but I would be surprised if they weren't carbon capture within 5 years.
So if you have a less energy efficient way of producing power, you're going to get more tax credit. If you burn coal per joule of electricity produced, you're going to get 3 times or twice the tax credit than if you're burning natural gas.
That is correct.
So this is just literally how many tons can you show you have in hand physically?
It's a production tax credit, yep. So there's EPA and Treasury guidance on how to measure and verify that and then claim that tax credit. So, I mean, that's significant. The other really significant one is the California Low Carbon Fuel Standard. This is California's overarching greenhouse gas reduction program, has a cap and trade for power and for transportation. Transportation one trades at over $100 a ton. It was $140 last week. The price ceiling is $200 a ton, and as that cap gets ratcheted down, it's expected to get closer and closer to that cap. So if ethanol is $30 a ton and somebody's willing to pay you $150 plus $50 more because they stack, that's an enormous economic opportunity. I think time will tell what the actual barriers are and whether the academic assessments of these $30 per ton projects bear out. But it's a very interesting time for the carbon capture industry in a way that wasn't 2 months ago. The other thing is that on the forest and soil side, there's been great progress. One of the biggest impediments to actually restoring our forests and planting more forests is the way that fire suppression worked is we were having more and more big fires, and so Forest Service had to use more of their budget for restoration and management to put out the fires. Congress just changed that. And so now the Forest Service can actually use the budget that it had for restoration to do restoration projects, not fire suppression. That's huge, and I think it will unlock a lot of new opportunities for forest expansion. The other piece is healthy soils. And as you remember, there's not a huge carbon opportunity in soils, and you can't put all of the atmosphere carbon into the biosphere or the soil reservoir overnight. But this is hugely important for, in my mind, political will. That as farmers see themselves benefiting from cleaning up carbon and making their soils healthier, more resilient, using less water potentially, all of these co-benefits are incredibly valuable as well. And so there are an increasing number of programs and interest amongst farm policy communities about these regenerative ag programs. So things happening. Business is also catching on. I think one of the things that we're seeing is there's a complete shift in the investment community around carbon tech. This is this idea of taking waste carbon, transforming it into something that you can then sell, as opposed to taking carbon and just burying it. Enhanced oil recovery is the big economic driver historically, but people are working on putting carbon into cements and other building materials, into fuels and chemicals and plastics. And there are some really interesting longer-term applications around how you put carbon into carbon fibers and use that for a range of applications. One of the interesting things we're seeing here is this links back to policy opportunities. California has an interesting program called the Buy Clean Act, which says that California must procure low-carbon materials. And there's an effort underway to expand that to include things like cement and carbon sequestering.
You mean the state's businesses?
Not the
Like
state's
the
businesses,
state-
the
the
state
government
itself.
The government.
Yeah, so California, the government of California is the biggest buyer of stuff in California. So it's actually a big driver.
Cement
So
requires an
this-
enormous amount of energy to make.
It does.
So why are you saying California, you focus, it sounded like what you were saying California was focusing on as a low carbon.
How to reduce the intensity of that. So capturing the carbon associated with cement production and or using waste CO2 to strengthen and reformulate cements. So it would sequester greater volumes. So it's a really interesting space. The X Prize has a carbon prize now. To show the potential of this, they created a shoe made out of carbon. It's the shoe without a carbon footprint. I think that's very clever. There are lots of emerging opportunities that I think you can buy a mattress in Europe, I think only, that is made out of carbon from a company called Covestro. You could buy carpet tiles made from carbon by Interface, a major carpet tile manufacturer. So it's not people that you would expect, but yeah, questions?
I'm not used to that phrasing. So when you say made out of carbon, you don't mean sequestered carbon. You
Waste
mean-
carbon. So they take a carbon emission source and convert it into a polymer and use that in their production, as opposed to using natural gas or oil or something else to make that polymer.
Okay. Can you give an example? I don't get it. Like, they're taking.
So-
like, not a gas, like not, I think, mostly flue gas.
Right, so the way you'd make plastic traditionally is you'd take natural gas or oil and you would refine that through a chemical manufacturing facility into a polymer and use that to make plastic.
Are you saying commercially they're making polymers from CO2?
Mm-hmm.
And they can do that because people pay such a premium to be able to say that their shoe is made out of CO2?
In that case, yes. I think there are a number of companies that are figuring out how to not lose money on these carbon conversion products. I know 3M is developing a process for carbon conversion. Yeah.
So would any, I mean, we're looking at this as a real possibility for limiting carbon emissions. Would any waste stream turned into polymer, turned into material good count? I mean, just wood pulp into.
Mm-hmm. Yeah, there's the whole bioeconomy, and if you could figure out how to have those sustainable bio feedstocks, yep, that could definitely fit in there.
So it doesn't have to be CO2 to fit into this ultimate goal of sequestering carbon.
It does not. CO2 is valuable as a pathway that you're likely not going to bury trees as a long-term carbon sequestration source, where you are likely to bury CO2. And so the extent to which you can create a market for CO2 that then, as policy ramps up, moves from shoes and buildings and whatever else to just a pure waste management business, that's an essential stepping stone. So the extent to which you can use CO2, it's thought of as more valuable for technology demonstration and market creation and policy creation. But yeah.
And I guess with that, so I'm the chemist in the room. So in terms of the value-added products that one can make from CO2, I mean, there's a fairly limited, I would think, set of polymers that one could directly take CO2 and do this. So I guess if people thought about how scalable that would be.
Yeah. So I think the biggest one is likely cement and aggregates.
Okay.
And that's thermodynamically downhill in most cases, so that actually is likely a better economic proposition to start with.
Gotcha. Yeah.
We use something on the order of a couple 100 million tons of plastic every year, so it's nothing to sneeze at, but it's not your gigaton scale solution. Things like carbon fibers, in theory, could be a big one, replacing structural steel and aluminum. You could get to the several gigaton per year level, but that's much more speculative at this point. I think the other thing is there's the regenerative ag seems to be this beyond organic movement, that as people are thinking about how do they make their supply chains more sustainable, food, fiber, all of these land-based materials, we're seeing the usual suspects in these spaces, Annie's, Patagonia, Ben & Jerry's, like the leaders on the sustainability front who adopted organics early are also adopting these carbon sequestering.
What's an example of regenerative ag? It's a new term for me.
So it's a broad umbrella of solutions both in livestock and in row crops that regenerate carbon in the soil. So it's that whole list of cover cropping and perennialization of crops and rotational grazing.
Okay, so it's about soil carbon, basically.
Yes.
Okay.
The other big one, I think, is the cross-laminated timber market. We're starting to see large buildings, 10 stories, order of magnitude, getting built out of wood. These cross-laminated timber structures are actually more fire resistant than some of the steel and cement equivalents, which to me was why we didn't build out of wood for the past 100 years or so. But I think this is an interesting opportunity to think about how we expand forests and actually create a market for forest products beyond simply paying people to plant forests.
Is the carbon sink from that building technique, is that primarily lack of cement, or is it the actual carbon?
Both. Assuming that the building will stand for a century. It's a well-constructed building.
Yeah. Do you have a sense of ratio? Are we talking 10 to 1, or are they about equal in terms of their impact on?
It really depends on what you're building out of. If you're replacing cement and steel, it's pretty significant in the avoided emissions.
Right.
And if your forestry is a sustainable, reforested area, then you also get significant sequestration if that forest is managed well.
Okay, I was imagining the actual wood in the structure is a place that you're sequestering.
Exactly. So that's where the sequestration happens. The sink happens through sustainable forestry. And then I think associated with each of those spaces is civil society, like really starting to pay attention. The NGOs have programs thinking about carbon sequestration. Foundations are starting to actually fund advocacy in this space. And that was totally different than even 3 years ago. This has really gotten on the agenda. I think a couple of things to watch out for is the IPCC is going to come out with their 1.5C special report. I showed you graphs for 2C earlier, 1.5C. The graphs look even more bleak. And I think many countries and advocates for climate think that that's the right target. And so if we really want to do that, we have to scale up carbon removal massively. We also have to scale up decarbonization massively and electrification massively, but it highlights and amplifies the role for carbon removal. The second thing is the National Academies is coming out with a roadmap. What should Congress fund, essentially, in this space? And that's a key question because people are excited about this. And they can't just fund direct air capture. They have to fund specific advances. Do we need new contactors and sorbents and systems engineering and integration into renewable energy systems that are intermittent and so forth? So there are a lot of these applied science questions left, and I think there is going to be an increase in funding for that. The last piece is the New Carbon Economy Consortium. It's a group of, again, about a dozen universities and national labs hoping to share its vision for doing some of this research and networking and connecting together a lot of the existing efforts in this space and thinking about what some of those bold goals that universities and labs could do versus what the feds could fund. And so this is going to come out in a couple months. Happy to distribute that with folks here as they are interested. That's all I have. Not too much information, I hope. Other thoughts or questions? Happy to go back and review any of those pieces in more detail. Anything on both the science about why we need this in terms of eliminating emissions and cleaning up, thinking through what some of these options are, as well as going into more depth on the policy or business and even the research elements that we're seeing.
Just a question about technological innovations. What is the patent climate right now for carbon sequestration processes and things like this? You know, are a lot of companies in there filing new patents? You know, has it been 18 months? And do you start to see patents in terms of different processes trying to capture that as a proprietary technology?
So I don't know,
Okay.
and I also don't see patents as being the key indicator of progress in this space. What I see as the key indicator is projects built.
Mm-hmm.
So the patents themselves are less relevant to me because people have been working on these patents for decades, and that has not translated into projects. So the extent to which we begin to translate some of those patents into projects, I think, is a more relevant indicator in the near term to show that this field is taking off.
It is an indicator, though, that some people hope to make a profit.
That's true.
Doing those processes, you know, otherwise there's no reason to file patents, right?
That's true. To me, this is really a early deployment problem as opposed to an invention problem right now. That you obviously need the pipeline of new innovation, but
Yeah. But sometimes the patents can slow innovation.
that is true as well.
You know, so it's important to know what the patent
Mm-hmm.
situation is. Yeah.
other thoughts, questions? My door is always open. You can find us at the Center for Carbon Removal. Feel free to shoot me a note. Happy to continue the conversation. Yeah.
The unit you showed us in Iceland, capturing it out of the air, wouldn't it be far more efficient and effective to put some sort of units like that on all coal and natural gas generators?
Yeah. It's a yes and.
Yeah, but we're not doing it, are we?
I think we're starting. That's what that.
I mean, it was a research unit, right? They didn't put it there because it was cost effective.
So they are selling some CO2 to a greenhouse in Switzerland. So they are selling at the 100-ton per year scale. So there are commercial units.
But I mean, like, someone's paying a premium for that unit. It's not cost competitive with buying CO2.
I think in that instance it is, that it costs a lot of money to truck in CO2 to greenhouses in Switzerland, but we're talking, yes, very niche markets. But you're right, this is the thermodynamically challenging end of the spectrum. That doesn't necessarily mean it's the economically challenging one. Regulations, customer perception, all of that, I think has held back these large point sources considerably. And you could see people sort of overpaying for air capture because it's more consistent with their long-term goals. But I agree that we should be sequestering carbon associated with coal and natural gas and industry and cement, glass, steel. All of those things are great point source opportunities. And I think we will not get to a place where the air capture matters until we have done all of the capture on those sources.
Soon industry fights it because there's no incentive for them to spend the money to put carbon capture units on their stacks for their power generation.
So they do have an incentive now.
They now have one.
Yeah.
Because for a long time they didn't.
Right. So that incentive was largely a product of oil companies wanting more CO2. So electric power companies don't want to force themselves to put on more pollution control. But the consumers of CO2 in this case were able to get a pure carrot. There's no stick associated with this. So cool. Well, thanks everyone. Let me know if you have any more questions, and yeah, glad to follow up.
Thank you very much. Excellent.
Is the salt water at the bottom of the ocean at great depth, is that saturated with CO2 already?
No.
Or is it, or could they